All right. Good morning, good afternoon, good evening, depending on where you're joining us. We bring you back the webinar on Kubernetes as a part of the series that we are running. My name is Janakiram. I run my own organization based out of Hyderabad in India. I'm a Google developer expert, primarily focused on cloud and containers. Joining me is Joseph Jacks from Aprenda. He's also the founder of KubeCon. Joseph would be joining us in just a few minutes. So let's get started while we have others joining in. So, as most of you are familiar, the Kubernetes webinar series is a monthly webinar series focused on helping you get started with Kubernetes. Our plan is to bring experts from the ecosystem who will walk you through a variety of concepts related to Kubernetes. And every webinar focuses on one concept and goes deep into it. So this is our third webinar where we are going to walk you through the concepts of pods and replication controllers. Previously, we covered the concepts of the architecture and getting started and setting up the environment of Kubernetes on your machine. Basic understanding of Docker would certainly help, and all the attendees would get $100 GCP credits along with some other goodies. The recording of this webinar, the slides and the source code that we are using for the samples will be shared with you after the webinar. We'll be sending you a mail with all the links to the resources for the webinar. So the objectives are pretty straightforward. We are going to take a closer look at the pods, which are the fundamental deployment units of Kubernetes. And we'll also take a look at multi-container pods. So multi-container pods are essentially a collection of multiple containers acting as one deployable unit. So we will take a look at that. I hope you're able to listen to my audio and also see my screen. Let us know if you have difficulties in following the session. You can always type a question in the question box of the GoToMeeting tool. So let me get started. But before that, like every time, I want to bring up a quick poll to just understand your skills about Docker and containers. So if you can take a minute and respond to this. Excellent. This is also a way for me to ensure that you're able to follow my session. Both the audio and video are reaching you. So that's a good confirmation. So it looks like most of you are at the intermediate level, with just 10% of you considering as experts. So that was the poll. Thanks for participating, and this gives me a good idea on how many of you are familiar with containers. All right, so let me close the poll, and now we have Joseph as well in the webinar. Joseph, can you briefly introduce yourself and kick off this?
Yeah, sure, no problem at all, Johnny. Thank you very much for having me. Very excited to be here again, and we've actually seen a great reception to these webinars, so I'm happy to participate. So yeah, as an introduction for myself, I've been very involved, very deeply involved in the Kubernetes project since pretty much the beginning, a little over 2 years ago, and have seen the project and the community grow. As you mentioned, I started the Kubernetes community conference, KubeCon, co-founded a company called Kismatic, and work now at a great company headquartered in New York called Aprenda. So I'm excited to be here, and happy to support answering any questions anyone has throughout and sort of at the end of the webinar. And provide some of my perspectives on these things. So, would you like me to cover some of these objectives, or continue to the next slide, Johnny?
We can get started with the next slide. So.
Okay, sounds good. So pods, as Johnny was saying, were in the previous objectives here are the sort of the atomic unit of scheduling applications in Kubernetes. And what a pod really represents is an abstraction that is ideal for what you could think of as a distributed systems abstraction or a cluster abstraction. So inside of a pod, we actually run multiple containers, or at least more than one container. There are some cases where you would run one container in a pod, but those are less common. So ultimately, we're running multiple processes or multiple containers that are tightly coupled or co-scheduled together in the same context. What that means is in a pod, all of those containers that are running in that pod actually share the same IP address that the pod has, so they can actually communicate with each other using localhost, which is a pretty nice feature. A lot of people will really enjoy that feature. Makes it very easy to very easily, transparently debug systems running inside of a pod or exec into a pod and see what's happening inside of a specific container, as well as swap out containers very easily that might be causing problems, or that might where you might want to change or modify functionality inside of a single pod. It's modeled like a virtual machine, so in the sense that each pod can contain multiple processes that are tightly coupled. Each container within a pod represents a single process. The way Kubernetes actually schedules pods is completely automated. There are ways to manually schedule pods on specific machines, but we encourage the design of Kubernetes strongly encourages the operator and the developer to simply tell Kubernetes that you would like a certain pod to exist, or a certain number of them in a certain configuration, and the system itself automatically makes that happen. So the user doesn't have to think about which specific machine a pod is deployed to. Pods are scheduled directly onto compute nodes in a cluster. So in a Kubernetes cluster of, let's say, 10 machines, you could have a pod deployed on each machine in the cluster, or you could have 10 pods deployed on each machine, and you can have 100 pods and that kind of configuration. So there's many different ways to actually run pods in a Kubernetes cluster. And again, this is the sort of the fundamental unit of deployment for running applications in Kubernetes. So at this point, Johnny's going to actually give you a live demo of running a pod in a Kubernetes cluster. So Johnny, I'll pass it over to you.
Cool. Thanks, JJ. That was a pretty good introduction. So, all right. So we are at the command prompt. And what I want to show you is creating a pod from the ground up. So we are going to create an Nginx pod all the way from the first line of the definition till we expose it as a service. So just to give you an overview, so we are running a Kubernetes cluster on my machine. So when I actually say kubectl get nodes, you see that I'm running a 4-node cluster with one master. So this is my current setup, and let me make sure I don't have any pods running. So that's a good start. So let me start my Sublime editor, and I'm going to create the definition of a pod from the ground up. So we'll call this my pod. So I'm going to switch to the Sublime editor. Okay, so basically every object of Kubernetes starts with an API version, which is typically v1. This might eventually change based on the beta or the alpha or the upcoming releases of Kubernetes, but that's the mandatory first line. And then the YAML file that we are using, which is the declarative way of interacting with the Kubernetes infrastructure, everything is described. Every object of Kubernetes is described in a specific format. So basically, pod is just one of the kind of objects that Kubernetes supports. So the next line that we're going to add is kind pod. And this is where you would actually use a service or a replication controller or a deployment or node. Even node is actually an object. So you can basically define all the Kubernetes objects in the YAML file in this format. So once we define what kind of an object we are dealing with, then comes in the metadata part of it. So metadata is very important because this is how Kubernetes identifies the objects. So every object should have a name. So let's call this my pod. And it can also have optional labels. So labels are additional metadata that you can associate with any kind of Kubernetes object. So for example, I'm going to call this app demo. The environment of this could be dev test staging. So I'm going to call this test. And that is the metadata that I am associating with this object, which is the pod. That's it. Now we are starting with the next section, which is called the spec. And spec is the most important section of any Kubernetes object. That is where you define the specification of an object. Since this is a pod, the spec is expected to have an entry for containers, right? So we'll put containers followed by a collection. So you can have multiple containers. So we are going to have the name of the container, which is going to be Nginx. Then the image that we are going to pull from the Docker Hub, which is also called the Nginx image. And then we are going to expose certain ports. And ports is again a collection. So you can have multiple ports, expose it from the same container. So we can actually give a name to this port, which is always a good idea in Kubernetes. And then we will define the actual port, which is the container port. And obviously we are exposing port 80. And finally, we need to define the protocol. So Kubernetes ports can be of type TCP or UDP. So that's it. So this is basically the definition of a pod in its simplest form, very minimalistic form. So starts with the API version, then the kind of object that we're dealing with, some metadata, followed by the actual spec that will contain object-specific specification, object-specific template. And let's save this, come back to the command prompt, and let's create from this YAML file that we just created called mypod.yaml. And there we go. So now we have mypod created. Let's go ahead and check that out. So kubectl get pods will show us that mypod is up and running. You can explore further by using this command called kubectl describe pod mypod, and this shows us a lot of information. For example, this container has been scheduled in the first node with the IP address ending 201. And since the image was already present, it completed the pull process pretty fast, and then it actually launched the container, launched the pod. So now that we have the pod, we are tempted to access that. But if you have been attending the webinars, you know that a pod is not exposed to the outside world directly. You need something called a service. I don't want to overwhelm you by talking about services at this point. We have a dedicated session coming up for that. But for now, let's use a command called kubectl expose. So you can pretty much take any pod and expose it to the outside world or within the cluster. So since I want to expose this pod to the outside world, even by connecting it to a domain or a CNAME or an A record, so it doesn't really matter. So I'm going to expose this to the outside world. So I'm going to expose this as what is called as the node port, which means one of the nodes of my Kubernetes cluster will be responsible for routing the traffic. So we are opening it up at the node level. The other type, which is the more implicit, the default type is cluster IP, but that will confine your pod pretty much to the same cluster. So more on that later. So for now, let's go ahead and expose this at the node port level. And now the service is created. Let's also go ahead and check the services. So you will notice my pod is now exposed as a service. But to really get the service port, So we are going to use describe service my pod, and this shows us a specific port number. Let's leave this here and let's pull the IP addresses of our nodes. So I'm going to call get nodes. So now I'm going to open the IP address followed by the port that our service is exposed on. And now when I hit enter, it basically opens up my default browser and it shows Nginx. That was the fastest demo that I've ever done on Kubernetes, because this included everything from starting a blank YAML file, typing all the way, then deploying it, and because the image was already pulled in all the nodes, it pretty much moved into the running state, and then we exposed it, and that's how we can access pods. So that is the simplest way of creating, launching, and exposing the pod, right? So this could be pretty much your first pod created on Kubernetes. Great. So let's get back. JJ, are you still here? Because I see your audio being muted.
Yeah, no, that was great, Johnny. Thanks for that.
Cool.
I think it just goes to show how powerful Kubernetes is. In a few minutes, you can create a configuration file describing your pod and the networking requirements, execute a single command, and actually be serving a web service essentially within a few minutes. It's pretty amazing. Well, really a distributed web service, because if that pod crashes or dies for some reason, it'll actually get recreated. So there's lots of facilities there that are really powerful. Going a little bit deeper here, describing what a pod is, we talked kind of about the fundamental abstractions, but there are some properties that are kind of important to understand, and the design here is very, very important, because it's one of the major building blocks for ensuring that a distributed system can actually operate reliably and in a highly available manner. So on the left, we have a small diagram describing or visualizing a few different things. So we have a service container that's basically pulling data from an external source, like a content management system of some kind, maybe pulling some files or doing some Git operation, and then we have a web server, perhaps serving some data to an external client somewhere. And so those two containers are actually very closely related to a single function, essentially. So remember we talked about how there are many shared resources inside of a pod. Well, in this case, we actually have a shared volume. So inside of that pod, those two containers that are serving data and pulling data can actually be sharing the same data volume, and multiple containers running there are actually able to use that same persistent volume for shared state. The thing to understand here is that if your pod dies, you do lose all of that data. So you want to make sure that as much as possible you keep your containers running in pods stateless, so that you don't risk data loss. To go through some of these points here on the right. Again, we've got a few things to kind of pay attention to. Again, we share the data volume. We also share the networking communication, as we discussed earlier, using inter-process communication, or IPC. We also have the containers within the pod inheriting the name of the pod itself. So there's name consistency. And of course, the IP address is shared in the flat networking space of all the containers running in that pod. So some of the use cases for the pod abstraction are as follows. I think we talked a little bit about content management, where we can actually serve data and pull data, doing file data loaders, cache managers. There's lots of different patterns that are really valuable here. You could dream up many more than are listed, I'm certain. You can do log checking and backing up logs, compression, rotating logs, snapshotting them. That's actually a really useful pattern for the pod abstraction. You can also have data changes. So when you might be pulling data from an application and serving it to another one, doing log tailing or monitoring. Event management systems are pretty useful in this context as well. And there's also sort of some additional patterns here that are more sort of cross boundaries or sort of cross-sectional patterns where you might have a proxy fronting a certain connection stream or offloading connections to a certain source or target system, and then bridging and adapting to another set of containers. So that's another kind of use case. And then finally here we have seen folks who are actually using certain pods for being controllers or managers of a certain part of an application, and then distributing or redirecting load to another set of pods that are related to those controllers or managers. So there's quite a few use cases here for the pod abstraction. Again, I think that the main fundamental design benefit is that you sort of get a lot of the distributed systems goodness for free by modeling your application in small components that are tightly coupled within the pod abstraction. And Kubernetes, if you sort of follow the webinar series and you learn more about the system, you can sort of understand that there are many pieces of the system that are decoupled from each other, very cleanly decoupled. And there are other parts that actually encourage a strong degree of coupling, where things are tightly integrated. And in the case of a pod, containers within a pod being tightly integrated and sharing resources is a good example of that.
Cool. All right. So as Joseph mentioned, there are multiple use cases for using containers, more than one container within a pod. And one of the things that I want to zoom in is the way we package a Redis cache container along with a Python container. So the use case is in a way modeled around the real world scalable applications. So to give you a visual representation of this, we basically have a database pod running MySQL, which is exposed as the cluster IP available within the cluster to another pod or a set of pods, which is the web pod. And every web pod essentially contains a Python Flask container and a Redis container, which is going to be the cache container. So the logic that we're going to use here is every time the Python container is queried for a specific data set, it first checks within the Redis container, and only if the data is not found, it will access the MySQL container via the service. So if the same Python container is responding to similar queries, it will completely avoid doing the round trip to the MySQL container because it can use the local Redis container. Now, when we actually launch additional number of web pods, we are replicating the pair of web container and Redis cache container as a part of the scale out or as a part of the replica set deployment. So the takeaway here is we are actually using 2 containers per pod, and when we scale them, we are launching at the multiples of two containers per pod. So they scale together. So for all practical purposes, they are one unit of deployment and one unit of scale. So every time we launch an additional web pod, we are directly launching a Redis container and a Python container. So I want to walk you through a demo that will give you a good sense of how to create multi-container pods and what are the popular use cases for using that. So let me bring you back to my command line. All right, so I have a very simple application here. So when I go to build, you will see I have an app.py followed by a Docker file, a Docker compose file, and a Python requirements.txt. So let's take a look at the app.py. So app.py is basically using the Flask framework of Python to expose certain REST API endpoints. So there is an API endpoint called init. Then there is an API endpoint for adding the users. And there is an endpoint to query and retrieve users. So I know this is not the best practice, but for simplicity, I have hard-coded the MySQL connection string. And the Redis connection string is retrieved from the environment variable Redis host. And only if this is empty, we'll use Redis as the host name. So within init, I basically perform certain initialization for our demo app. Like we create a sample database called UserDB, and we populate that with a set of users. So that is the init method. And after that, we basically use a get request or the post request to add users. So this is where we insert into the database, and that is the add endpoint. And then there is get users, which is the endpoint meant for retrieving the users. And the assumption here is there will be more number of read operations than write operations. So every time a value is retrieved, it is assumed that it hasn't changed since the last updation. So the use case is we populate millions of users and we'll retrieve their details, but not very often the data would be modified. So here in get users, we basically check if the key is available within the cache. If it is available, we append the data with a C and return that as the output. If it is not found, then we go ahead and query it from MySQL. And in that process, we also push it to the local cache, and we set 36 seconds, which is very short, but for the demo, this is fine. So we set an expiration window of 36 seconds, and then we return the value. And this is listening on port 5000. So this is a pretty straightforward, very simple Python Flask application. Now I can go ahead and use Docker build, followed by my Docker hub name, and I'm going to use some kind of a tag, but that is not the point. I have already done all the plumbing. The Docker image is built. It is already pushed to the Docker hub. All of that is in place. Now that we know what is the application, and by the way, this application has no clue where it's going to run, whether it's running in Docker data center or Mesos or Kubernetes. It is an application. It could have been running on my local host with just Python followed by app.py. It doesn't really matter. But now we'll actually take this application and deploy that in Kubernetes. So let me show you what I have here. I have a set of YAML files. So let me open all of them in my editor and then walk you through each of them. So the first one is the database pod. Pretty straightforward. It's a MySQL container exposing port 3306, and we are passing an environment variable which is password, because this is what is expected when we are bootstrapping the MySQL container. And once the container is in place, we go ahead and expose this as a cluster IP. So this is going to be available within the cluster on port 3306. And this is the service endpoint for the web pods to discover. After that, I go ahead and create the web pod, and this is where it becomes pretty interesting. So you're familiar with this. We have already seen the definition of a pod, but within containers, you'll actually notice that I'm using two different containers. The first container is the Redis container exposing port 6379, which is the standard Redis port. And then we also have our Python container, which is being pulled from Docker Hub. And this is where it gets pretty interesting. So the Redis host environment variable, instead of passing anything else, I'm actually passing localhost, because the Python pod and the Redis pod are sharing the same namespace, which can be resolved using localhost. So I pass localhost as my host name, though it is running in a completely different container. But thanks to Kubernetes and the concept of a pod, I can pretty much treat like Redis is running within the same namespace, within the same local host. So we then expose the container port 5000. This is the default port of Flask applications. And once we have the pod in place, then we go ahead and expose a service. And again, the service is going to be exposed at the node port level, which means this is available to the outside world. There is no user interface to it. It is basically an API endpoint. So this is not going to have any user interface that we can access to the browser. So we'll use curl for all of this. So that is the basic model where we have taken the Python application, built a Docker image out of it, and then we are creating multiple pods and multiple services and deploying them in Kubernetes. All right, so let me also launch my helper script, which would help me with all the commands that I need to execute, which will just make my typing a little faster and easier. So I'll also have this ready. All right, so now we go to the multi-container pod, go to deploy, and start deploying our app. So first thing, kubectl create from file dbpod.yaml. So this is going to create our MySQL pod. So once we have the MySQL pod in place, obviously we need to expose that. So now we are going to create the service. So service is the intermediary that connects the other consumers of this pod at runtime. So now we have the MySQL pod as well as the MySQL service that is created. Now we'll also go ahead and create the web pod 1.yaml. So this is going to create the combination of Redis and Python containers, and then we go ahead and expose the web service to the outside world. Okay, let's grab this value. We need it later. So I'm going to take this and save it in my environment variable here. All right. So now what you see on the screen is pretty much all the steps that you need to deploy this application. So we started with the DB pod, exposed as a DB service. Then we launched the web pod, and then we exposed that as a service. So let's go ahead and check if everything is in place. So get pods will show us the older my pod. Actually, let's get rid of that. We don't need it anymore. So delete pod, my pod. Similarly, we'll get rid of the service that we created earlier. We don't need them anymore. So now when you actually do get pods, it's pretty straightforward. We have MySQL pod, and the most interesting aspect here is 1 of 1. That means there is only one container in this pod. Whereas the web 1 pod is showing us 2 of 2, which means there are 2 containers in this pod. So when we actually say describe pods, it will show everything related to it. And now if you actually look at web 1, that is assigned to one of the nodes, which is 201, which is the first node of my cluster, and it pulled Redis, then it pulled my custom image that I built from the source. So now we have everything in place. So what I'm going to do now is to set a couple of environment variables just to make it easy to access them. So this will represent my node IP and node port. So I'm going to use curl to initialize my database. And this will show me that the database is now initialized. This is actually the first step that we need to perform. And then what I'm going to do is to add a couple of users. So I'm going to add a user called John Doe with user ID 1. And I'm calling the Kubernetes endpoint that is exposed. And I'm making a post request to this endpoint, and I'm adding the first user. So the first user is added. Now I go ahead and add a couple of more users, right? So we'll have at least 4 users that are created. Perfect. So now we have populated the database, through the REST API that's exposed through the Python Flask application. Now, when we actually do a GET request on users, first time it shows John Doe. Nothing special, no rocket science. But when I invoke this again, you see a C getting added to it. That means this was pulled from the Redis cache, and all subsequent requests are pulled from the Redis cache. Similarly, let's access the second user, Jane Doe, right? All subsequent requests are hitting Redis and not MySQL. That's pretty cool. And the key thing to understand here is every Python container is coupled with a Redis container, and they are running together. So now let's actually do something interesting. So I'm going to create another pod, which is a combination of these two containers. So I have exactly the same definition, but it is called webpod2.yaml. So let's go ahead and create this. So now when I do a get pods, you'll actually see that this is the other pod that we just created. It will take a while depending on how long the image will take to get pulled. So I have pre-pulled all the images to keep it quick and a swift demo. So now we have two web pods and one MySQL pod. So let's go back and retrieve the users. So now I'm going to retrieve the first user, and we don't see a C. Two reasons. Number one, maybe our request has hit web2, which doesn't have the cache, or the cache window of the first pod has expired. But let's give it another shot. Yeah, so maybe the cache has expired. So even if it is hitting the first pod, it is still retrieving from MySQL, but all subsequent hits will basically grab the value from Redis cache, right? So this is an indication that we have tightly coupled containers packaged as one pod running together. And in the next demo, we'll actually go ahead and scale the number of pods to 20, and we will come back and repeat the same query, doing a GET request from the endpoint, and we'll see some interesting results. So stay tuned and let me get back to the slides and walk you through the next set of concepts in terms of the replication controllers and replica sets. Awesome. So replication controller is a very powerful concept of Kubernetes. So we have seen launching one single pod. And later on, I have also gone ahead and launched another pod with the name Web2. That's always good to have a redundant pod which can take over in case your first pod crashes. But what if Kubernetes gives you a primitive, an infrastructure level object that can always maintain the desired number of pods? And that's replication controller for you. So what it basically does is it maintains a certain number of pods based on your definition all the time, ensuring that at any given point of time, the number of pods match the definition of the replication controller. If one of the pods gets killed or gets crashed, the replication controller's job is to bring it back to make sure that the desired count is always the same as the declarative state. So every time a new pod is launched through a replication controller, it is under the observation and the control of the replication controller. If that gets killed or crashed, replication controller will automatically resurrect another pod. So that's the beauty of it. It's actually a good idea and a best practice to create a replication controller with a count of 1, which means that even if the only pod that is running gets crashed or gets killed, replication controller will bring back. If you're familiar with Amazon's EC2 auto scaling, I have seen customers deploying auto scale with min is equal to 1, max is equal to 1, even if they are not scaling out. And that is a fault tolerant mechanism to ensure that at any given point of time, you have at least one instance of your application available. And the same logic applies to a replication controller. It's a good idea to launch pod always to a replication controller with the count as 1, even if it is just one of the pods. And if you're wondering how a replication controller picks the appropriate set of pods, it uses the concept of labels and selectors. So remember, when I created the pod, I added metadata and I added a label section to it with 2 different labels. I said app is demo, environment is dev or test. Now later on, when I'm actually creating a replication controller, I can say this replication controller is responsible for monitoring all the pods that match the tag app is demo. And this is going to ensure that all the pods with the appropriate label are associated with the selector of the replication controller. So that is the matchmaking mechanism of Kubernetes. This is very simple yet very powerful because the labels, which are the metadata or the tags associated with the objects, are used for discovering them at runtime through the selectors. So when we actually see the definition of a replication controller, it would become pretty clear. But Kubernetes is advancing pretty fast, and with every release there are new concepts and enhancements and augmentation to the core platform. So one of the more recent advancement to replication controller is called as a replica set. For beginners, they're almost the same. I don't want you to get confused because this is one of the most ambiguous concepts of Kubernetes. But a replica set is different from a replication controller in just 2 simple forms. Number 1, the way a replica set identifies pods is through annotations. So annotations is the next generation of labels and selectors, which will use some advanced query mechanism to associate the objects at runtime. For example, with labels and selectors, it's always a binary. It is either is equal to or not is equal to. Whereas with annotations, you can include pretty complex conditions to make very granular decisions at runtime. You can't use those annotations and complex queries with replication controllers, but you can pretty much do that with a replica set. That is the first difference. The second difference is replica sets are the preferred way of using or rather deploying pods through another declarative mechanism called a deployment, which we'll cover in the upcoming webinar. So deployment is a very mature way of rolling out your applications, and replica sets are aligned with deployments. But if you're a beginner and you want to get familiar with the concepts, I would strongly encourage you to understand pods first and then replication controllers. Replica set is just an incremental update to replication controller. So if you don't understand the difference, don't get confused. It's totally fine if you're a beginner. We'll be covering labels, selectors, annotations, and deployments in the upcoming webinar. So for now, just stay focused on the replication controllers. So now it's time for us to take a look at replication controllers and replica sets and scaling out our web pods. So let me come back to the command prompt. And here we have exactly 2 pods that we created, and both of them are created manually. As in, I went ahead and executed kubectl create from file command twice to get these 2 web pods up and running. So if I kill one of the pods, for example, let's go ahead and get rid of web 2, nothing happens, as in Kubernetes will simply delete that pod. But what if I want to run at least 2 pods all the time? That's exactly where I bring up a replication controller. So let's take a look at the replication controller definition. So here you would notice the same familiar statements or the semantics, but instead of a pod, we are using a replication controller. And then there is metadata, which is also common. And then the spec starts. So within spec, there is something called replicas, which is 10. Let's make this 3. Okay. And then right after replicas, there is a template. And within template, you actually see nothing but a pod definition. Right from this up to this point, it is essentially a pod definition. So I have copied and pasted exactly the same. So if you look at this all the way from metadata till this, sorry, I need to show you the web pod. Yeah, from metadata till the protocol, we pretty much have the same definition here. So this is nothing but a pod template which is embedded inside the replication controller. The only difference is we mention the desired state of replicas as X, and Kubernetes will ensure that at any point of time we have those many number of pods running. So let's go ahead and execute this. So now we have just one pod, which is web1. So now I create the replication controller from the definition that we just saw. So replication controller web created. So now when we actually say get pods, you will notice that two new pods have emerged with a random arbitrary name attached to them. So though I mentioned 3, Kubernetes was smart enough to figure out that there is already one that is available, and it has just gone ahead and created 2 more pods. And if you're wondering how did Kubernetes get to know that we are running one pod already, because it matches the same metadata that we mentioned in the replication controller. Any pod that matches the metadata will be counted as a part of that deployment or the replication controller realm. So it is already included in the definition, so it has only created 2. Now let's grab one of this and delete it. So now I'm going to delete this pod. Okay, so now when we do get pods, even before I executed this command, the replication controller is trying to bring back another. So now in just a few seconds, we'll actually see the other one coming up. Once you have a replication controller, it's also possible for you to scale them. For example, you can use this command called kubectl scale replication controller called web, and the number of replicas is going to be 20. So now I have scaled out my deployment to 20 pods. Imagine doing this with your virtual machines running in a typical IaaS environment. This would take ages. 20 instances of your application in just a few seconds. So that is the beauty of Kubernetes. Now, when we are running all the 20, you can actually go ahead and start executing our commands. For example, let's go and grab the first user. Now, you will not see the cached output very often because it is hitting one of the 20 pods that may not have the cached data. So you never know which of the 20 pods is responding to your REST API. So that's the pretty cool thing about Kubernetes. Scaling from 0 to 20, and all the pods are in running mode. And every pod has a combination of a Python Flask container and a Redis container. So that's the power of a replication controller. Now, you can also use the same command, kubectl scale RC. The name of the RC is web. Number of replicas is just 1. And now we have scaled out our deployment, and we are back to square one, where we just have one database container and one web container. At this point, you can also safely delete the replication controller called web. Oops, looks like something went wrong with my cluster. Okay. Okay, so something suddenly happened with something went wrong with my cluster, but that's not a problem because we are almost done. I'm so glad that I could finish all my demos before this message appeared. So no problem, we are almost done. So that was the demo. The good news is I have something to share with you. Um, you can pretty much access the entire application on GitHub. When I'm going to send you the mail over the weekend, you can actually run this entire thing on your local cluster or in Google Container Engine. Remember, we're going to send you the $100 credit for spinning up your GKE cluster. So you can pretty much run the same demo that's available on GitHub, and you can experience exactly the same environment and the walkthrough on your machine with a working Kubernetes cluster. Excellent. So, okay, where are my slides? Okay, come on. Okay, there we go. So sometimes my browser acts funny. All right, so we had a pretty detailed discussion around pods and replication controllers. So to do a quick recap, pods are the smallest unit of deployment in Kubernetes, as Joseph has been articulating. It is a fundamental deployment unit in Kubernetes. One pod can contain one or more containers, but at least one container. If you're already familiar with containers, think of pod as the wrapper on top of the container. But that wrapper can be home for multiple other containers, not just one. Replica sets are the next-gen replication controllers with additional capabilities. But the core concept is replication controller, which will ensure higher availability of the pods. So the entire script and the sample application along with the Docker build file is available on GitHub, and you will receive the details over the email when I send you the link to the recording as well as the GCP credits that you can redeem. So that was a very quick walkthrough. Now on November 23rd, we are going to take a closer look at services. So if you are noticing, we are digging into the concepts, we are getting into the depth, and this is where the real fun of working with Kubernetes will start. So I'm pretty excited to get into the depth of Kubernetes. So the next session would be on services, where we understand how service discovery works in Kubernetes, how you expose multiple pods as internal only services, external services, how to use a load balancer, what are the best practices, and in that process we'll also take a look at the networking stack, how exactly the service translates the virtual IP address, how does it route the request from the consumers to the providers. So it's a very fascinating concept. So you can go ahead and sign up for this right away. If you like today's webinar, feel free to sign up for the upcoming one in November. Typically, we host this in the last week. So go ahead and sign up. Stay tuned for that. And at this point, I want to pull up one final poll just to get your quick feedback. So really appreciate you taking a minute and responding to this poll. All right, the results are pretty encouraging, but I see only few of you are participating. I appreciate if all of you can just click on one of the options based on what you felt about attending this webinar and investing time in this. We really appreciate it. Excellent. Thank you very much for sharing your feedback. It's very encouraging, and we'll continue to bring you detailed, qualitative content around Kubernetes, one of the fastest growing open source projects in the history. So stay tuned, and thanks again for attending. We are now going to address a few questions. JJ, are you able to shortlist a few, and do you want to take up a couple of them?
Sure, definitely. So we actually got a question about pods and the number of containers deployed. So a question was, in which circumstances can we use only one container per pod, or any suggestions here? So I actually have a use case that comes up quite a bit in terms of pods that are just executing a single operation for maybe a batch process or a short-lived process, like running something on a cron style scheduled time period, or just a single ETL run or something like this. In those cases, you might want to run a single container in a pod and just run that pod to the completion of that task, and then kill the pod. I don't know, Johnny, do you have any things that come to mind for running a single container in a pod?
Yeah, so most of the cases where you have a very granular microservice kind of a deployment, where you want to make sure that the deployment works in any other environment, because the pod concept and the whole primitive of bringing multiple containers as a single pod is very specific to Kubernetes. So if you are modeling your application for Kubernetes, that's great. But if you want to make sure that your container deployment works in any other environment, other orchestration engines, other container as a service platforms, you might want to keep them loosely coupled, where you will align one container per pod. So that's the motivation behind using or not using multiple containers within a pod.
Yeah, that's great. I would agree with that. So we have another question on how does Kubernetes with the replication controller actually help with zero downtime deployments? We got that question from Venkat. So Kubernetes replication controllers can absolutely help with zero downtime deployments, in actually making sure that your service is reliable and up and running with a very specific number of copies in the cluster. So if you have a few of those pods crashing or dying for some reason, the replication controller will actually create new copies of those pods and make sure that it's available. And in the case of actually a rolling deployment, or a zero downtime rolling deployment, you would actually use an object called a deployment object that actually controls a replica set, which Johnny covered a little bit. And that's more of an advanced pattern and use case for doing a rolling deployment. But yes, you can absolutely use replication controllers for zero downtime deployments in that way. We actually got a few other questions. Do we have the ability to control where a pod runs in the cluster when it is created? That is a very good question. You absolutely do have that ability. Kubernetes provides some pretty flexible controls for doing this. With labels and selectors, you can actually make sure that a pod is deployed on a very specific node in your cluster. There's another type of replication controller set called a pet set, which gives you this functionality as well. I think in future webinars we can cover that and go into a little bit more detail as well. So it looks like we've got a bunch of other questions here. I don't think we have time for all of them, but we can certainly follow up over email. You can just drop an email over to, correct me if I'm wrong, Johnny, but just info@kubernetes.live. We should be able to get back to you on many of these questions. Let's see, affinity rules for container creation so that a set of containers can be placed and managed together at any time. That's a really good question. There are a few ways of doing this with some options in the community. There are service catalog, service registry projects out there like Helm with Helm charts that allow you to describe a collection of pods that need to be run as part of a single sort of service, integrated service, and you can create an inversion and run those types of objects in Kubernetes. Johnny, did you have anything else to add to that sort of multi-pod container affinity types of patterns?
No, actually, so as long as you want both the containers to be co-located, you package them as a single pod. If you have specific requirements that a pod should be scheduled on a specific node, you can use labels and selectors, as Joseph mentioned. And that is how you bring in affinity at multiple levels. Containers running in the same pod, pods running in the same node. You can do all of that using the labels and selectors.
Right. So I'll just do rapid fire on a few of these questions that Tiago Jayaraju was asking. These are very good questions. So does an outage to a Kubernetes master node cause the container access or container service outage as well? The answer is no. You can still access the services and containers with the master node being unavailable. Another question is, does Kubernetes support other container runtimes other than Docker, and can they coexist within the same cluster? Yes, the answer is yes. So you could have some nodes in the cluster that actually support running Docker and other nodes that support running Rocket or other container runtimes. Another question is, does Kubernetes pull images from regular Docker registry repos? The answer is yes. Another question is, does Kubernetes support automatic resource management within the cluster? Absolutely, the answer is yes to that as well. So there are some pretty advanced facilities for controlling CPU, memory, and disk resource allocation for the containers running in a pod, as well as the containers running or the pods running in a namespace portion of the cluster or the cluster overall. So there's some pretty powerful controls there. Just going through some of the other questions here. Let's see. I think maybe, Johnny, you can answer this one. Is it a good idea to run MySQL or any other database in a pod?
Yeah, so I'm seeing a lot of questions on why not run MySQL and the web container together, either in the same pod or actually as multi-container pod. So it's always a good idea to separate stateful containers with stateless containers, because stateful containers have very stringent requirements. For example, I might want to have an SSD-based storage that is mounted as a volume. So I want the database to always co-located, or rather scheduled, on the node that supports the SSD storage. And moreover, I'm not going to use a replica set to scale a SQL server or a MySQL container like the way I would do it for a web. So the requirements are slightly different. So you got to be cautious when you're modeling your stateful containers and stateless containers. So when you apply the concept of a replica set to a stateful container, you essentially have what is called as pet set, but that is still an evolving concept. As of now, you got to have a clear strategy the way you run stateful persistent containers like databases and stateless ephemeral containers like web servers and cache. All right, looks like we are almost at the end of it. We are running out of time. Thank you again for joining us. And Joseph, thanks so much for joining me and co-hosting this webinar. Really appreciate it. I just got a feedback from someone that November 23rd is a Thanksgiving Day, and that's not a good time to have the webinar. So we will revisit that, and I will announce the next webinar very soon. Watch out for an email as a follow-up, and you can sign up for the session. Thanks again. Have a great weekend.
Thanks, everyone.
Thanks, JJ.
Bye.
Bye.